saying? This is what's really gonna make me like, you know what I'm saying, be more concise and all of those things.
This space. But it's really concise, right? If you type this into idle, you should see the kind of list that it returns. And also what list comprehension is now, what now constitutes list comprehension.
Alright.
You can use list comprehensions with functions like map and filter and reduce. And along with anonymized functions, all of these tools provide you with a lot of functionality in a very short amount of space. It's also good to be able to recognize what's going on when you see something like this, or something like this. Because you probably run into it in particular, a lot of Lisp code, but also in the artificial intelligence community in particular. Okay. We talked about all that. Let's take a second to talk about the fact that lists are actually mutable, and what that means, and what things you have to be careful about if you're going to be working with mutable objects.
Yes, mother.
If you're new to programming, or you're new to Python, you've probably already worked with some of these data types, right? Any numbers, any strings, any tuples are going to be immutable.
So you can also
what that means
raise it on the screen?
If you have a variable, and you have a second variable that has
I'll show you later, as long as it's good now.
Associated with it, right? I haven't assigned G to H here. I've just assigned G to hello and H to hello. If you look at the space in memory that Python associates with both objects, they point to the same place. This is the definition of an immutable object. When G points to hello and H points to hello, they both point to the same place. If X points to 5 and Y points to 5, they're both pointing to the same place. If you point X at 6, it now points to a different memory address. This gets confounded when you're talking about mutable objects. The problem with mutable objects is that you select a memory space to contain the object, or memory ID in Python to contain the object, and then that object is changed in place. You can use this to your advantage, but it can also mess with you, and here's how. Let's say I assigned, A to a small list, and I also assigned B to A. B and A now point at the same place. If I manipulate B, and I'm, still working with an immutable object, if I'm still working with a mutable object, the object in that memory address has been altered, and B and A still point to the same place in memory. So if I look at A, it's going to look like B, which is going to look like 1, 2, 3, 4, which is not what I assigned A to originally. Again, can be powerful, but you have to keep it in mind, and it might start to mess with, in particular, the 601 software when you're dealing with state machines. In order to get around this, you can create a copy of the list and then modify the copy. This is actually what map does. If you want to do it, the easiest way to do it on the first layer is to specify the index into the list with no bounds. It'll copy the whole thing. There's also a Python library, copy or deep copy, if you want to copy lists of lists of lists of lists of lists. And just to clarify, you'll note that after you assign C to a copy of A, C and A occupy different memory places. So if you modify C, A will retain its original value. I think that's all the notable things I have to say about Python, and gives us enough power to do some really powerful list manipulation or array manipulation, and covers what we want to say about functional programming before we get into the notion of state, which I'll talk about next time. Hi, today I'd like to talk to you about state machines. State machines are an incredibly important concept, both in 601 and in the general sense when you're going to be doing things like control theory or artificial intelligence, or any further work you do in terms of computability theory. State machines are really important. So I'm going to review what we've done so far and talk about why we now need state machines to add additional complexity to the kinds of models that we're going to build. And then talk a little bit about how state machines are represented in different domains, and then also talk about how we're going to use state machines in the 601 software. First of all, let's review what we've learned so far. We've talked so far about functional, imperative, and object-oriented programming paradigms. In functional programming, everything is a function. In imperative programming, we're allowed to use functions, but they're also allowed to have side effects. And in object-oriented programming, everything is an object. We can actually use the first two to implement the last one, and use the first one plus, an idea of maintaining assignments to variables, that sort of thing, to implement this one. So you can sort of trace the progression of different kinds of computer science languages along this paradigm. But the one thing that none of these languages on their own allow us to do is keep a notion of internal state. And what I mean by that is that if we have a system that we want to model in terms of the passage of time, or keep track of the evolution of that system, or keep track of some of the data that has accumulated over time in that system, then we certainly can't do it with functional programming, right? Functional programming takes one input, generates one output, and you could generate a function that you could generate a list of code that took in every possible, every possible situation and then generated the logical output, but that would be a lot of code. Same thing for imperative and object-oriented programming. Them alone do not address everything that we want to address, which is the ability to look at as a consequence of the passage of time, and all of the data that we've looked at as a consequence of the passage of time, synthesize it in some way, and then generate either, whatever is supposed to come out of that situation. That is the notion of internal state. State machines have been around for a while. You might see them referred to as discrete finite automata. There are also such things as continuous state machines, but we're not going to talk about those in this course so much. So we're only talking about discrete state machines, and when you see them referred to as state machines or discrete finite automata in literature, especially in mathematics, you'll be looking for this 5 set of things. One is a set of the possible states you could be in given a particular state machine. One is a set of inputs you could possibly encounter while in that state machine. One is a set of outputs that state machine could possibly generate. One is a transition function that looks at pairs of these values and tells you, based on which state you're currently in, what state you will end up in as a consequence of the current input, and then also specify what the output will be as a consequence of that transition. And finally, it'll tell you where you start out. That's a lot to absorb. I'm going to show you a state transition diagram, which many of you have probably seen before, and map these values to the state transition diagram in hopes of making this a little bit more concrete. Hopefully at this point, all of you have interacted with an MBTA turnstile. This is the thing that opens and closes, and you stick your RFID card on it, and then Richard Stallman yells at you and possibly hands you more Charlie tickets or something like that. It has 4 states. One of them is that this turnstile could be closed, and it's waiting for people to interact with it in some way. It could be open, and what I've, anthropomorphized the turnstile as being happy as a consequence of you putting money in it. It could be open and quiet as a consequence of usually some sort of other previous interaction with another person. Or it could be open and angry as a consequence of people interacting with it when they should not. The vertices in this directed graph are my set of states. So when you see something like this, and you're asked to map it to the mathematical construct, just grab the names and say, this is my set of states. Let's say I start off in closed, and actually it occurs to me that the other thing that should be specified is a start state, and it's not here. So let's say the turnstile starts off as closed. Usually this is an arrow coming out of nowhere that directs into one of the states. Sometimes it will be explicitly indicated by saying start state, but typically you'll just see an arrow, from nowhere. At this point, I don't have any inputs or outputs. If I put money in the turnstile, it constitutes input to my system. It's going to end up in my set of inputs for math. My transition function looks at the state I'm in and looks at the current input and generates the output and the next state. So all of these arrows, in addition to whatever information is contained in the receiving vertex, specifies my transition function. Any transition that's not specified is not considered in the function, right? This was not part of our original drawing, so if I was fed open angry, there would be no way to get to open happy. Likewise, if I was in open angry and fed money, for this simple system, we're going to say nothing would happen. I think at this point, it's become clear how to transform a state transition diagram into the mathematical constructs. It's good to have the mathematical constructs because they end up being used in software, which I'll talk about in a second. But the first thing I'm going to do is just walk around the state transition diagram and indicate what would be inputs, what would be outputs, that sort of thing. So, let's say I walk up to the turnstile, and somebody else interacts with the turnstile by exiting. In this case, exit is the input, none is the output. The turnstile doesn't make any noise. And the turnstile is open. If at that point, I interact with the turnstile by entering, it's going to make noise, which is the output. And then the new state is going to be that the turnstile is open and angry. At that point, you and I know that the turnstile is going to close. So this edge indicates that the only available input at that point is to do nothing, or independent of anything else. It's going to swak again and close. One more time. Here are the states. Inputs are the first of these two pairs. Outputs, as a consequence of the transition, is the second of these two pairs. And the transition function is represented by the directed edge and the new state. Once you have all those sets figured out, you can start talking about how to implement state machines in software. We've actually abstracted this away from you. You don't have to deal with it. But as a consequence, you should know how to interact with the 601 library. Let's look at an example of the state machine class. I want to build an accumulator, which at every time step will look at the input, add it to every other example of input and output, and then output the new value and retain it as the new state. The first thing I need to do is initialize the accumulator with a value. This is our start state, which is the same as our start state from the MBTA turnstile, and also the same as our start state from the mathematical construct. I also want something called getNextValues, which is the functional equivalent of the transitions. Here's ourself again from object-oriented programming, but we don't care about that. We're going to look at the current state and the current input. Some getNextValues will do some internal data munging, right? Possibly multiplication by 2, or comparing to the previous input and then having some conditionals, that sort of thing. But there'll be some sort of very simple function under getNextValues, at least for the first couple weeks. And then we will return the new state and the output in a tuple. In this case, the new state is going to be the linear combination of the current state and the current input, and the output is going to be the linear combination of the current state and the current input. If I were to draw this accumulator as a state transition diagram, I would do this. My start state is the initial value. If I pass in a new input, we'll call it input 0. Both my output and the new state are going to be the linear combination of these two values. If I made another transition, I would take whatever my next input was and add it to the current state value and return it out as the output, and so on and so forth. I encourage you to try this in Python, or I guess in idle, and munge around with it and see what you can get it to do. You might have to type add lib601 in order to get the state machine class, or initialize using lib601 in order to get the state machine class. But otherwise, this should be enough to get you started with the introduction to state machines. If you're having trouble, I highly recommend going through all the examples in the readings. They're pretty comprehensive, and it also includes the accumulator. That's all for now. Next time, we'll talk about linear time invariant systems.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hello and welcome. So last week we started to think about programming. Programming was the first module in this class. And it was important for two different reasons. First, we're going to use programming throughout the term in the study of all the different things that we do. So it's important that you learn to program now just so that you can use that tool. More importantly, perhaps, we didn't just learn how to program. We focused on how to program in a fashion that would let us construct complicated systems out of simpler systems. This is a way that we can manage complexity. This is the only possible way that we can make complicated systems. So that was the more important intellectual theme from the first part, where we introduced our mantra, PCAP. Primitives, means of combination, abstraction, and identifying patterns. That's the key to this modular approach to hierarchical kind of design. Today what I want to do is start the second major theme. First theme was the design of complex systems. We saw that by reference to programming. Today we're going to start thinking about modeling and controlling physical systems. The idea here is not so much how you construct systems, but we will get back to that. The idea is to characterize the systems that you've constructed and say something about their metrics as being positive or negative. So what we want to do is, in fact, focus on behavior. So to illustrate that, I'll start with an example. This is an example that you did in Design Lab last week, or for some of you yesterday. The idea was to program the robot so that it could sense the distance to a wall, represented two ways here, sort of the view that you would get from SOAR, and a more schematic representation showing the position of a robot, the position of a wall. The idea is that you can sense the position to the wall using the sonars. You know where you would like to be because some user told you you'd like to be, say, half a meter away from the wall, and your job was to move the robot, write a program that moves the robot from where it is to where you'd like it to be. So here's the kind of behavior we might have liked. So I'll do that again. So we might have liked that if you started here, you'd have a nice, smooth progression up to where you'd like to be, very graceful, ballet type, and you just sort of smoothly glide into the position that you'd like. Some of you probably achieved that behavior, and some of you probably did other things. So, but that might be the intended behavior. One way to achieve the intended behavior is to use what we call a proportional controller. In a proportional controller, you make the command be in some way proportionate to the intended response. So imagine this code, which might establish a class for finding the wall. So the important thing, as we saw for all state machines, the important thing is to define a start state and a get next values routine. What this get next values routine does is it establishes the desired distance to be a half a meter. It figures out the current distance to the wall by reading the sonars, and then it specifies an action. So the first question is, what would you like fval to be in order to make a proportional controller? Which of those expressions makes sense? Take 30 seconds, talk to your neighbor, figure out some answer between 1 and 5. I will ask you in 30 seconds to raise your hand with that number of fingers. So what's the right kind of expression if we wanted the controller to be proportionate? Everybody raise your hand, show me some number of fingers. Okay, the vast majority is saying 2. Everybody likes the idea of current minus desired. Why is that the right answer? That is the right answer. Why is that the right answer? How do you prove that to somebody? Yeah?
Current divided by desired, once you reach your desired distance, then you're still going to have the total velocity of 1, which really doesn't make sense.
Exactly. So that method we might call extreme cases. Think of the simplifying cases that give you some insight into the problem. So one simple case is, what if desired and current were the same? You'd better stop. Okay, that's a simple case. So the simple case says that you better have one of these, whatever the right answer is, it better have the property that when current equals desired, f val is 0. Otherwise, it's not going to work. And in fact, using just that one simple case, you can eliminate all the ones except 2. There are some other simple cases. What are some other simple cases? Simple cases, yeah. Current bigger than desired. So if current were bigger, that would mean that you were starting out way over here someplace. So if you were way over there someplace, you'd want the velocity to be positive. The forward velocity should be positive. That's how you would disambiguate the sign, right? Similarly, if the current were shorter than desired, if you were too close to the wall, you'd like the forward velocity to be negative. Okay, so that's the proportional controller that we'd like. So we might fill in our wall finder class this way. And then when we built it, if things went really well, we would get exactly the behavior we wanted. But if things went more naturally, it wouldn't quite work that way. And you might get a different kind of behavior. Let's do that again. So here's the resulting behavior for that simple controller that I just showed. So in some sense, that's not as good behavior. And the way we want to think about behaviors, the way we're going to develop today, is to think about behaviors in terms of signals. Plots. So the first question is, what plot best represents the behavior that I saw here? So which of those plots best represents that behavior? Take 30 seconds, talk to your neighbor, figure out what's the right answer. Okay, so which behavior best represents the illustrated cartoon that I showed previously? Raise your hand, show some number of fingers so that I can see if you're with it. Not all correct, but more than 90% correct. The more than 90% answer is number 2. What's good about number 2 that's not good about numbers 1, 3, and 4? Yeah. Initial is different. So here we're showing initial and final being roughly the same. So what's showed here is a plot, current distance on the y-axis, step number on the x-axis. And so we can see from here, and the implication of the axes, by the way, is 0. So the implication of the vertical axis is it intersects this at 0 unless I label it otherwise. And similarly, this horizontal line intersects the vertical at 0 unless I label it otherwise. So that's the point 0, 0. So the implication here is that the initial and the final values are the same as they are here. Here they're not. What makes 2 better than 1?
Yeah.
Yeah. The current distance starts out bigger than it ultimately is. So we start out bigger than the final value. The final value is presumably half a meter. We start out roughly twice that far, and then we see some approach. The approach is not monotonic. So the answer is 2. Why do you think it undershot? So on the way to going from 1 to a half, it transiently went through something smaller than a half. Why do you think it did that? Yeah.
It's a small beginning time where it's going to
So there's a small interval of time between when it does one thing and it does something else, when it senses and moves, for example. So there could be a time delay in the system, and in fact that's true. There is a time delay. So it takes some amount of time for the sonars to register the distance. Then it takes some amount of time for the computer inside the robot to register that the sonar is told it something different. Then it takes some time from the time the computer commands the wheels until the robot starts moving. All of those cumulative effects mean that you have the potential to overshoot where you're going because there's delay in the system, there's inertia in the robot. All of those reasons can lead to overshoot. And the point of today is to figure out some way of predicting and correcting for those kinds of unintended behaviors. So what we will do then is develop an approach focused on signals, not systems. So far we've been thinking about how do you build the system. Now we're going to think about behavior. We're going to think about analyzing that behavior. And the focus is going to be on what was the input, what was desired, what was the output, what was achieved. So we're going to be looking at those output signals in order to figure out how good the behavior was. That approach is called the signals and systems approach. The idea is characterize your system, whatever that system is, a physical system, a mathematical system, a computational system, whatever it is, think about it by the way it transforms an input signal into an output signal. That's kind of a bizarre way to think about systems. So let me just illustrate that by way of a system that you've all seen before. Okay, here's a simple system, right? You've all seen this, right? Anything like 801 ring any bells, Okay, so that's a simple system. You all know how to solve it. There's a gazillion ways you could solve this system, right? Free body diagrams, kinetic energy, potential energy. There's a gazillion ways you could do it. You all know how to do it. That's not the point. The point is that we're going to learn a different way to solve it. We're going to think about the mass and spring system not like potential energy and kinetic energy, not like free body diagrams. We're going to think about it as transforming an input signal into an output signal. So the input signal, it's kind of arbitrary what I decide the input and the output, but clearly the thing I have control over is my hand. Okay, so it seems natural to associate a variable with the position of my hand. That would be x. Also seems natural to associate a variable with the position of the mass. That could be the output y. That's not unique. Every time we try to solve a problem, we ask ourselves, what's the meaningful input? What's the meaningful output? The meaningful output could have been the force on the spring. Okay? I'm just sort of arbitrarily saying, for the purpose of my analysis, I'm going to consider the input to be the position of the hand, the output to be the position of the mass, and I'm going to think about the mass and spring system as a box that transforms x into y. So rather than thinking about it in terms of free body diagrams and kinetic energy and potential energy, I'm going to think there's some input signal x and there's some output signal y, and what I'd like to do is, given x, calculate y. Okay, bizarre. Why would I do that? One of the reasons I want to do that is that it's a very general way of thinking about behaviors. It works for the mass and spring system. It works for water tanks. What happens if I have water flowing into a tank that's leaky? Well, it leaks into another tank which is leaky, and that leaks more. Completely different physics. Probably wasn't covered in 801. probably is something you could figure out. The point is that from the signals and systems point of view, I'm going to map this physics, whatever it is, into this structure. Think about the tank system as the system that transforms some input. The input is that there's water spurting for some small interval of time. The output is that there's water coming out. And the idea is that I'm going to characterize the system, whatever it is, as the rule that transforms the input signal into the output signal. Here's a third example. I could think of a cell phone system. Here again, there are very complicated ways we could think about the system, but I'm going to take the particularly simple approach, called signals and systems, that I'm going to characterize the phone system by the way it transforms some input sound into some output sound. And as you can imagine, there's a way of thinking about performance in terms of that transformation. Ideally, we would like this to bear some resemblance to that. So the point then is that we're going to focus on behaviors, and to do so, we're going to think about the signals and systems approach, represent a system, whatever it is, by the way it transforms inputs into outputs. One of the reasons we like the approach is that it's so general. So you can use it for virtually any kind of a system for which you can develop a mathematical underpinning. You can use it to analyze electrical systems, mechanical systems, optical systems, acoustic systems, biological systems, financial systems if you're on the dark side. So there's lots of different kinds of systems that are amenable to this kind of approach. Also, this approach has a nice modularity. Having represented a cell phone by a transformation from sound in to electromagnetic field out, as illustrated by this cartoon depicting sound going in and having a radio wave transmitting to a tower, then we represent tower-to-tower communication some way, maybe via an optical fiber, maybe via a satellite, then tower-to-cell by the same kind of reverse transformation that we used in the first one. We can piece those all together. We can treat them as modules because each box takes an input signal and makes an output signal. The method is oblivious to the underlying physics. That affords a certain amount of power. And in particular, it's very modular. You can put together modules that represent very different physical substrates. That allows us to go back to PCAP. If the underlying representations for the different physical substrates are the same, we will be able to, and we will over the next 3 weeks, develop a bunch of techniques for combining multiple modules into one. That provides the same kind of abstraction and modularity that we saw in programming for the last 2 weeks. So that's the idea. What we want to do is represent a system by the way it transforms an input signal to an output signal. There are many different kinds of inputs and outputs, but a fundamental distinction that we are going to have to make is continuous time and discrete time. This system works in what we will refer to as continuous time because my position of my hand is a continuous function of the continuous variable time. The robots, by contrast, work with what we will call discrete time, steps. It turns out the math for those two different approaches are very different, and we will focus entirely in this class on discrete time because our area of application is the robot. It's not that continuous is deeper or harder or anything like that, it's just different. So we'll focus on discrete time. And the point of today then is to develop some representations for signals and systems of the discrete time nature that will let us analyze and predict behaviors of systems like the robot system. The first class of methods for representing such systems is difference equations. Difference equations are a lot like differential equations, except there's no differentials, there's differences. Difference equations are the discrete time analog of differential equations for continuous time systems. Simplest possible example here. Say I have an output y that, for reasons that I don't care about, I know can be represented as the difference between two values of the input, x at time n and x at time n minus 1. That's a way to represent the behavior of a system, a discrete time system, by using a difference equation. That's in fact almost a complete description of the system. So let me just explain the way you would use that. It's almost because I didn't tell you anything about the input. I'll tell you something about the input for the purpose of example, where I'll use the simplest possible input that I can imagine, something that we'll call a delta function. A delta function is a signal. It's a discrete time signal. It has the value 1 if the time index is 0, and has the value 0 everywhere else. It's in some sense the simplest possible signal that we could imagine. So it's natural to start there. So what I want to do now is think about if this were a characterization of the system, and if this were the input to that system, what would the output be? That's, after all, that was the question that I posed at the beginning. We would like to build a representation for a system so that we can predict the output given the input. So how does that work? So given the difference equation, all we need to do is step through it. Okay, it's trivial. We call that analyzing by step. So given the difference equation, given the input signal, all we need to do is sequentially go through the different values of n and think about the implication of the system on that input. So if I were to use the value of n being minus 1, this general form of the difference equation tells me that the minus 1 value of n for the output is related by this difference with the input. So y of minus 1 is x of minus 1 minus x of minus 2. Since both of those are 0, it says that the output at time minus 1 is 0. Trivial, right? Trivial. And similarly, we can just iterate through the solution to the whole signal. So y of 0 is x of 0 minus x of minus 1. X of 0 is that special one that is 1. So now we get 1 minus 0, which is 1. Y of 1 is x of 1 minus x of 0. Now the special one is on the other side of the minus sign. So the answer is minus 1. Y of 2 is x of 2 minus x of 1. They're both 0. And in fact, all the answers from now on are going to be 0. So what I just did is a trivial example of, I used a difference equation to represent a system, and I figured out the output signal from the input signal. That's the method that we call, that's the representation for discrete time systems that we refer to as difference equations. Difference equations are very powerful. As we will see, of all the representations we look at, difference equations is the most compact representation. But there are features of other kinds of representations that are also valuable. So the next representation I want to look at is a block diagram. What I'm trying to show here is a picture, a diagram, that represents the same system that we just analyzed with difference equations. Here, though, I'm thinking about it as a signal flow path. I'm thinking about what's the cascade of operations that you need to do on each sample in order to get from the input to the output. So the difference equation said every value of the output should be equal to the corresponding value of the input less the value before that. I represent that in a block diagram by saying there's a straight through path. Y of n is equal to x of n. The plus just adds the signals on these two paths. So y of n is equal to x of n. Subtract out, because I'm multiplying by minus 1, delay, so I'm getting the one from before. So this block diagram just is a symbolic representation of that difference equation. The value of the block diagram, we'll see several of them, but one of them is focus on signal flow path. If you want to visualize the transformation from input to output, the block diagram can provide insight, visual insight, into what that transformation is like. So as before, if I gave you this representation rather than the difference equation, you could still, step by step, and figure out the way it worked. It's still easy. There's one new caveat here. We'd have to start the system in a state. The state that we will usually talk about is what we will call at rest. At rest just means all the outputs of all of the delays are initially 0. So that specifies the state of the system at the time the signal is turned on. So the system is at rest, which means that all the delays start out with an output equal to 0. So at rest means this delay has an output of 0. Well, if I tell you the output is 0 at time 0 for this delay, then it's a simple matter of stepping through what is the output for each corresponding input. So if the special value of the delta function is that it's 1 at the time 0. So at the time 0, there's 1 coming in. That 1 makes it through the adder, adds to 0. Well, this is 0 because it was at rest. So the 1 adds to 0, and the output becomes 1. Notice that the 1 also goes down this path and goes through the gain of -1 to give me -1. But I'm in step 0. So at step 0, the output of the delay is 0, not -1. So the output then for time equals 0 is y equals 1. Just like we saw for the difference equation. After all, I'm hypothesizing that those two systems are the same. It better give me the same answer. So then at the next instant, as the time index goes from 0 to 1, two things happen. The input goes from 1 to 0, and the delay box gets updated. The delay is now reporting to me the value that was at its input. So the output of the delay, which had been 0 because it was at rest, becomes -1. So then what happens? The 1 goes to 0, the 0 goes to -1, the 0 adds to -1, and we get an answer which is -1. Then the input becomes 0. That 0 comes down here, the -1 goes to 0, we end up with 0 being added to 0, and the next answer is 0, etc. So the idea then is that you can step through the block diagram representation just like you would a difference equation. It's just that now we're thinking about these blocks characterizing the system rather than thinking of math as characterizing the system. Why on earth would you do that? What's good and bad? What's the relative merits of difference equations versus block diagrams? Take 30 seconds, talk to your neighbor, figure out some good feature of each. multiply. Okay, we'll start with the easy one. What's a feature, what's a property of the difference equation that makes it very good?
Jesus.
What's good about the difference equation? Yeah.
They can be solved mathematically.
They can be solved mathematically. The block diagram could be solved, maybe not mathematically, but kind of. Could you refine that a little more? What's special about difference equations that's different from block diagrams? Oh, what? I said it.
Use math.
They use math? Yes. They're concise, they're little, right? It's a very simple expression to say that. It's by contrast a bit more complicated to draw this picture, right? It's mathematically concise, right? It's completely accurate, self-contained, concise, small. It's a very concise representation of a system. So why would we want to use block diagrams? Can anybody think of any good reason for block diagrams other than Freeman's up front saying do block diagrams?
Electrical engineering.
Electrical engineering. There should be a deeper reason, I would hope. I don't disagree with that reason. Why do electrical engineers like this? Yeah.
It's a more like physical representation of the system.
It's more physical. Is there anything that you can see in this that you can't see in math? Yes?
And the way that you're actually going to be programming it, like, you're going to make a delay machine, you're going to make a state machine that multiplies it by -1, and you're going to see how to connect them.
That's a really good point. It's kind of isomorphic to the implementation. Everybody get that? It's kind of a picture of the way you would build the system. Along those lines, there's some bit of information. There's actually more information in this one than there is in that one. There's exactly one bit more information in the block diagram. What's that bit? Delay? There's kind of delay by the n-1. Yeah. The input and output are explicit. Yes. The errors are the big difference. You can't tell from the difference equation what's the input and the output. You can tell from the block diagram what is the input and the output by the direction of the arrows. So there's more information in the block diagram. There's another way of thinking about it, and this is kind of a summary of several comments that came from the audience. The difference equation is declarative. It tells you a true statement about what the system will do. The block diagram is imperative. It tells you what to do now. Take the input, put it into an adder. Take the input, multiply it by -1, put it into a delay. Take the delay output, put it into an adder. The representation with a block diagram is imperative. It tells you what to do. So there's extra information, but it comes at a cost. It's a more complicated representation. It's a whole picture instead of just an equation. What we'd like to do, and what I'm going to do now, is develop a different mathematical approach where you get a different equation that has the same properties of concision, the same conciseness, but also contains all of the information that was in the block diagram. And the way to do that is to change our focus. And this is the big abstraction of the day. Change our focus from thinking about samples to thinking about signals. Stop thinking about x of n. Start thinking about the input signal x. This is the same kind of lumping that was key to abstraction in Python. Put all the interesting data together into a list. Put all the interesting operations together into a definition. Here, put all of the interesting samples together into one signal. So what we want to do is develop a math by which we can operate on signals instead of samples. So what I'm going to do is replace the representation x of n, little x of n, with cap x. Cap x means all of the n's. It's the signal x. Cap y means the signal y. And I'm going to reinterpret all the boxes. This box means take this signal, the whole thing, all n values of it, multiply it sample by -1, flip the whole signal upside down.